In Chapter 3, we're going to move forward with describing quantitative data. So in the previous chapter, we talked about qualitative data, and in this one, we're going to be talking about quantitative data. Because in the last chapter, we ended off with the visualization of qualitative data, I want to continue that and move on to the visualization of quantitative data. So that means taking a look at different types of graphs and plots that we can use to graph our numerical data points. And then after that, we'll summarize how we can use statistics to calculate numerical measures for the data sets that we have. So that would be like the mean, median, and mode, or measures of spread, standard deviation, as well as measures of relative standing. So let's start off with an overview of quantitative data and our approach to describing it. First, it's the fact that we now have numerical information instead of just frequencies. So that means we have to deal with either discrete or continuous variables, and there are different ways of presenting that. We can describe numerical data in two ways. One is graphical, one is numerical, and we can either choose one of each or both types of analysis. How do we choose? Sometimes it really depends on how many data points you have and what you're trying to convey to your audience. If you have a lot of numerical data points, then a graph will definitely help show the spread of your data, and maybe you can try and describe the distribution itself, the shape of the distribution. But if you have a lot of different samples and a lot of different data sets, then having too many plots will cause confusion. So summarizing that through a statistical table after you've done some numerical measures may be more convenient. If you have key summaries, you can always summarize all of that into one final graph to show key trends and distributions between different data sets. But in terms of general statistics and numerical measures, I would try to recommend keeping that to the discussion so that you're not bogging people down with too much data in a chart without context. So let's start off with plots for quantitative data. We're going to go through pie charts, bar charts, and specifically line charts. Then we're going to take a look at histograms and relative frequency histograms, and then how we can interpret graphs and describe distributions. So we already talked about pie charts and bar charts, so I won't really go through them in detail, especially the code, because you already know that from the previous lecture. With pie charts, it's very useful when you're displaying a breakdown of numerical ranges. So if you have a continuous variable, and let's say you're trying to measure the temperature throughout the day, then you can set it so that you have different temperature ranges that are categories that your values can fall into. If you're taking a look at a bar chart, then you can also use that for frequency within numerical ranges. Most importantly, we'll be focusing on the line chart. If you are collecting data from numerical quantitative variables, it makes sense to plot points on a line chart and see if there's a line you can draw through them to model the distribution. So a line chart is very useful for trends across a time series or anything that grows along an x-axis that will allow us to predict patterns. So there are multiple examples from the notes, but just to describe this, I have some dummy data. Obviously, if you do experiments, you're going to have your own data that you can load through a text or CSV file. But to create dummy data, I can create my own time series. Basically, from points 0 to 10, I create 50 data points. And then I am going to have some live values with those time points. So then I would go from NumPy. I would have np.sine of time to calculate all of the sine values for each of the time points that I've created from linspace. So I now have 50 x values and 50 y values, and I can now generate a plot. So remember our object-oriented approach to plotting. We have we can create the figure and the axis at the same time, and then we're going to plot onto the axis time and our y values. And then I'm going to use a blue dot to plot those points. So over here, you can see those points that I've created are over here, and I've plotted those points throughout the domain from 0 to 10 for time. But if I do want to connect the dots, I plot another line onto that graph. So I'm going to do ax dot plot one more time, the exact same information, my time values on the bottom, my y values for the vertical, and then I have a red line that's plotted. So now I have the dots to represent my data points and a line going through them if I know the function that models these data points. And of course, at the very end, you can do plt.show to show the figure, the axes, as well as the plots. But some suggestions that I do have, even though you have, and even though you are able to plot the points and plot the line, make sure you always label your axes. Make sure you style your markers based on what you're looking at, especially if you have multiple data sets you want to plot together and you have bivariate data. That's something we'll talk about later on. You do have to make sure you use different colors or create a legend if you're using different styles of lines, just to be able to differentiate between different data sets. Okay, on to histograms and relative frequency histograms. A histogram is basically like a bar chart. The only difference is that you're binning your data into numerical categories. So if I have a bunch of data over here and I've collected them and they are values, then I can say maybe from 0 to 10, I have these values that fall within this range. And then from, I believe that's 0 to, and then in the middle, you have a certain number of values that fall into this range. The only thing is this a frequency histogram or a relative frequency histogram? We're going to take a look at both of them. The Python code to create a histogram is fairly simple. The first line you don't have to worry about because I'm just creating dummy data. If you were to do this for an assignment or a practice problem, you would be given the data set. We create the figure and the axes using plt.subplots. And the code for this is actually plt.hist or ax.hist for the histogram. And you're going to plot your data points x. You're going to create 12 bins. And you can also create an edge color, because when you plot all of your histogram bars, they're usually side by side, and it's very hard to tell them apart. So you can create an edge around each of those bars. So it would actually create a line around this rectangle, and you can choose the color for that as well. So that's some styling that's very useful when you're trying to differentiate between the different vertical bars for the histogram. But is it really helpful? Sometimes. In most cases, we would actually want the relative frequency histogram, and it helps us determine the distribution across our data set. So the proper Python code would be to make sure you create the bins yourself. So you have bins coming from 0 to 101, let's say, and you want 10 bins. Then you're going to define something called hist for your histogram values, and then edges so that we are sure where each of those bins end. We use np.histogram to define your histogram values coming from x and to define where your bins are, which were determined from here. So after that, you can calculate your relative frequency values by making sure your individual histogram values here, which is x, is divided by the sum of the number of values that you have. That will give you your relative frequency, and then you can plot not a histogram, but a bar graph with bins, your relative frequency, a certain width to your vertical bars, whether you can align the bars center to the tick mark, or on the left or on the right, and to make sure that you have a certain color for your bar graph. So that would be how you would plot a relative frequency histogram. The most important part is defining the bins, defining your values and edges, and then calculating the relative frequency. Now, is there a shortcut? Yes, there is. We're going to go through that in some of the practice problems and assignments. Next, how do we interpret graphs? So distributions are extremely important when you're trying to describe a graph, and it's really determined by its shape. So some things we can look at are symmetry, skewness, and what kind of distribution we have and how many peaks we have in that distribution. If I take a look at the right, I have one peak over here and then another peak over here. This tells me I don't just have one mode, I have two modes, and that gives me a bimodal distribution. Sometimes you may have a multimodal distribution, but in most cases that we'll be looking at this term, we'll be looking at the unimodal distribution. When we focus on the unimodal distribution, symmetry and skewness become very easy to spot. We're going to start in the middle, where from your data set, you have your mean, your median, and your mode. If all of them are in the same spot, that means there's an equal number of values above and below that spot that is your mean. Not only that, you have an equal number of values of certain magnitude on each side, and that gives you a symmetrical distribution and a perfectly normal distribution. If you have data sets that are slightly skewed towards one side, towards the right or the left, you then have a negative or positive skewed distribution. So for the negative skew, which is skewed to the right, you have your median over here, your mean is still here, and then your mode is shifted towards the right. That gives you a negative skew. And if it's towards the left, you have a positive skew. So that's just some terminology to be familiar with moving forward, especially when you're describing your data sets graphically. Now we want to move on to numerical measures for quantitative data. There are three main numerical measures we want to look at. They're measures of center, spread, and relative standing. So these all include terms that you should be very familiar with based on lab experience or just going through different classes. So although graphs are useful for visualizing a data set, they're not always the greatest tool when you want to make predictions about the population from your sample. So that means we have to be able to present numerical statistics to represent our data and to make inferences about that population. So using our data sets, we can calculate a set of numbers that will give our audiences and our readers a good picture of how our data is distributed and how accurate they are. So measures of center, the mean, median, and mode are the most popular measures of center. We'll start off with the mean, which is basically the average. If you have a set of n measurements, then your mean is the average or the sum of all of your measurements divided by the total number of measurements. Assuming xi is the ith measurement for one of our variables x, we can define the sample average as follows, like this. So x bar means average is equal to the summation of all of your x values divided by the total number of your x values. Now keep in mind, x bar is used for a sample, and you can use mu for a population. In most cases, we are going to be using the sample version of these equations. With Python code, if you use NumPy, you can quickly calculate the average from your data set, which is loaded up over here, either as a list or an array. You can define the sample average as np.mean of your data, and that just gives you your average immediately. For the median, from n measurements that you have, your median m is going to be the value of x that's in the middle after all of your x values have been organized and ordered from smallest to largest. So we can do that using NumPy as well. We have np.median, and that gives you your sample median. And finally, with mode, that gives you your most frequently occurring x value or category. You can use SciPy for this, and specifically the stats module from SciPy, and you can use stats.mode of your data. Something important with this is that stats.mode gives you the value of your mode as well as how many times it occurs in the list. So just make sure when you present your data, you're calling the appropriate value from sample mode after you've called this function. So let's say your mode is 5 and 5 occurs 20 times, then it would be stored as 520. So you would have to call the first number of index 0 to share the value of your mode, and then you'd have to call index 1 of this variable if you want to present how many times it took place. For measures of spread, we have range, deviation, sample variance, and standard deviation. So I want to start with range and walk you through the entire process of deriving standard deviation and why we have the equation we have today. So for the range, simplest thing that we can start off with is the difference between the smallest and largest values within your data set. It's called R, and it is a difference. So first, we have to calculate our sample max. You can simply use from Python the function max, and it's going to give you the maximum value from your data set, either a list or an array. Min of data is going to give you the minimum value from your data. So your sample range is simply just sample max minus sample min, and that will give you the range of your data presented as a difference. Now, speaking of differences, maybe we don't want to find the full range of our data set. Maybe we want to take a look at how much each of our values varies from what should be standard in our data set. So one of the most common measures of center is the mean. So from the mean, we can try and figure out how much each of our data points is separated or spread out from its center or mean. We call that the deviation, how far away a singular measurement is away from your mean. So we define it as xi minus x bar for the deviation. Now keep in mind, if you have a population, you would use mu for the mean instead of x bar. So follow-up question, what would the total deviation be for an entire sample or population of measurements? First of all, if you have your center of measurement here and you have your deviations going this way, let's just say they're going to be negative deviations because they're moving towards the negative side of your center. And over here, you have a positive deviation for all of the values because they're moving towards the right side of your center. So if you add all this up, you have an equal number of negative values and an equal number of positive values away from your center. So the total deviation for an entire sample or population of measurements should be 0 because they cancel each other out. So when we're trying to average the deviations, it doesn't really help. So that means we have to sum the squares, or at least square the values so that we force them to be positive. And then we add them all up to get a sum of squares. At the very end, we can take the square root and get our standard deviation. So moving forward from sum of squares, that fixes the fact that the total deviation is basically 0 if we add them all up. We move on to sample variance. For sample variance, the idea is that we sum up all of our sum of squares of deviation, and then we divide by the total sample size. So that part makes sense because it's almost like we're averaging all of our deviations through sum of squares. The only difference you'll find is this n-1. So I'm going to start with the discussion of population versus sample. If we're trying to calculate sample variance, if we're trying to calculate variance from a population, then we already have a complete picture of the population. We don't have to infer statistics for the population because we're already there. So that means if we have our deviations and we sum the squares, we're going to divide by capital N because we already have all of our measurements, and it gives us a fairly accurate representation of the variance of our population. So in that case, we use sigma squared for our population variance. When we move on to sample variance, we're taking a subset of the data from the population. And so even if we do calculate the variance like this and divide by n instead of n-1, we still get a variance, but we've significantly underestimated the error. So to fix that, we subtract 1 from the denominator to make our sample variance larger. And that helps in getting a better estimate of your population variance. So that's a key difference between the two that you should be aware of. And another term that I'm going to present is something called bias. So if I were to ask you, why is there a difference between using capital N for population variance and n-1 for sample variance, then your answer should be, we do not want biased data. If I take an entire population of measurements and calculate variance, then I'm quite confident in my variance. But when I take a small subset of that population, a sample, and calculate variance, then it's likely I underestimated my variance, and I have to fix that bias by making the denominator smaller to get a larger overall variance. And by doing that, I create an unbiased sample variance. So moving forward, we can now look at standard deviation, which is taking your sample variance and square rooting it so that you get back your overall average deviation. So the positive square root of variance helps measure the amount of variation. It's simply this. If you have very low values, it means that your samples are very close to the mean. If you have high values, it means that your data is spread very far apart from your mean. There's a very quick way to calculate standard deviation from Python using NumPy, but we have to be very careful based on what kind of standard deviation we're looking at, whether it's for the sample or for the population. So we'll start off with this. The standard deviation for the population is equal to np.std of data. So very short piece of code. This gives you the standard deviation for the population because it automatically assumes that you have 0 degrees of freedom in your argument. The next line of code, standard deviation for my sample, which I just abbreviated to SPL. I have np.std of data with a degree of freedom of 1. This 1 basically tells me I'm subtracting 1 from the denominator for my variance. So this gives me the standard deviation for sample. So when you're doing your assignment or when you're doing problems or data analysis in the future, if you have a sample and you're trying to calculate the standard deviation, make sure you're using the appropriate degree of freedom for your calculation so you're presenting an unbiased variance and deviation. So when do I use this sample or population? As scientists, usually we use sample because we're always doing experiments or collecting data based on a subset of the population so that we can make predictions about the population. So based on that, it makes sense that the majority of the work we do will be based on samples. So just make sure you check your code and your syntax to ensure the proper functions or equations are being used for whatever application you're applying it to. Okay, next we want to move forward with measures of relative standing. With measures of relative standing, we have z-score and percentile. These two are very important when we're trying to describe our data. Starting with z-score, it's defined as x minus x hat over s. It tells me the distance between my observation and the mean based on standard deviation. And when I present information, it will be my z-score is, let's say, 1.6. That means it's 1.6 standard deviations away from the mean. So how do I know whether my point is an outlier or not? It depends. You can either choose to have most of your observations lie within 2 standard deviations from the mean, in which case your z-score would be less than 2. Technically, based on distributions, 95% of your observations will lie within 2 standard deviations from the mean, and almost 100% of your observations will lie within 3 standard deviations from the mean. So if you want to be safe, any data that is over 2 or 3, specifically 3 standard deviations from the mean, or if you have a z-score greater than 3, then most likely it's an outlier from your data set. So this gives us some sort of comparison to determine what data we're going to use and proceed with for our data analysis. So using the stats module from SciPy, the z-score can be easily calculated using stats.z-score. And that will just give you the value of z-score for either a large string of values or for a specific value that you're looking at. Okay, so now we want to take a look at percentile. So percentile has everything to do with the distribution itself. I have presented here a box and whisker plot, but I first want to just go through how to define percentile. If you have a set of n measurements and they're ordered based on magnitude from one side to the other, your pth percentile is going to be the value of x that marks a point where there is greater than p% of the measurements on the left side and less than 100 minus p% of the measurements on the right side. So if I am looking at, let's say, the 60th percentile, then the 60th percentile is marked here, let's say. And so on this side, you have 60% of all of your values. So this mark is greater than 60% of all of your values. And then this mark is going to be less than the remaining amount of your values. So basically, as you move along your distribution, you go from 0 to 10 to so on and so forth, up to 100% of all of your measurements. One of the greatest ways of presenting percentiles is through a box and whisker plot. Now, I won't cover this until we move on to data analysis, when we actually have data to explore and graph. But if you want to visualize percentiles, the box and whisker plot is very useful because, first of all, it represents the median. And this median is right in the middle of your data after it's all ordered. Your lower quartile marks 25%, your median marks 50%, and your upper quartile range marks 75%. So when you have your lower quartile, it's the spot when you have 25% of values less than that spot and 75% of values greater than that spot. You can use the exact same method for Q2, which is 50%, and Q3, which is 75%. The whiskers themselves represent the full range of your data. So if I were to actually draw this out, let me just try and get a pen over here. If I were to draw this out on a distribution, let's assume a normal distribution like this. It means that I should have this being my Q3. Let's just assume this is going to be Q. Oops, made a mistake. This would be Q2. This would be Q1. And then this would be Q3. So on your box and whisker plot, what would happen is you would take a look at this, and you would have this for the box and whisker with all of the whiskers going towards the full range of your data. So that's a good overview of percentiles, as well as what the percentiles at different quartile marks mean, as well as how a box and whisker plot represents that data quite well. Finally, we want to go through a summary of what's most important from this lecture. Obviously, we were able to describe quantitative data. You should be able to do it graphically and numerically. When we're talking about graphically, it means if I give you a data set with numerical values and quantitative data, then you should be able to plot a line chart or a relative frequency histogram based on that. Moving forward, we might look at scatter plots and density graphs, but those are things that will come based on the application itself. In the latter half of the lecture, we took a look at numerical measures for quantitative data. So we should be able to use Python code to quickly calculate these values and use them in our results. And then, of course, we want to understand the definitions of various statistics for quantitative data. So make sure you know how to do all of this before moving on to the next chapters.